You know, when you're staring at a huge, messy data set and just wondering, how do I find the hidden patterns in all this? Well, today we're going to talk about an amazing technique that does exactly that. It literally brings order to chaos. Let's dive in. Okay, take a look at this. On the left, you've got this raw, totally unorganized data. It's just digital chaos, right? But then, on the right, you see that exact same data, but it's beautifully ordered, revealing these really clear groups and relationships. So the big question is, what's the magic trick that takes us from that mess to this clarity?
Well, the secret is a really powerful data science technique called hierarchical clustering, and at its heart, it's an incredibly intuitive idea. All it does is systematically find and group similar things together, building this whole structure of relationships right from the ground up.
So, technically speaking, hierarchical clustering is an unsupervised algorithm. All that means is it finds these patterns all by itself, without you needing to tell it what to look for. It builds this amazing tree of related groups, or clusters. And honestly, here's the best part. You don't have to guess how many groups to look for beforehand. The algorithm just lets the data show you its own natural structure, which, trust me, is a huge advantage.
But how does this actually work? Well, the most common way is called agglomerative clustering. I know, it sounds a little complex, but it's really just a simple bottom-up approach. Think of it like building with Legos. You just start with all the individual pieces, and then you start connecting them one by one.
The whole process kicks off super simply. Step 1. Every single data point, let's say we're looking at 4 different chains, starts out as its own totally independent cluster. Everybody's on their own at the very beginning.
Okay, next, the algorithm scans all the points and asks a really simple question. Which two of you are the closest neighbors? It measures the similarity between every single possible pair to find the most alike duo. And in our little example here, it turns out genes 1 and 3 are the most similar.
So, step 3 is the merge. Since genes 1 and 3 are the closest, the algorithm just fuses them together into a brand new single cluster. And from this point on, the algorithm's going to treat this new pair as just one thing.
And then, you guessed it, it just repeats. The algorithm finds the next closest pair. In this case, it happens to be genes 2 and 4, and it merges them. This just keeps going, merging the next closest clusters again and again, until eventually, everything is grouped into one single, giant supercluster.
Now, this whole process seems pretty straightforward, but there are actually 2 really crucial decisions you, the data scientist, have to make that will totally guide how the algorithm behaves. So let's take a look at what they are. All right, the first big choice we have to make is this. What do we actually mean when we say closest? The algorithm needs a very precise mathematical rule to measure the distance between any 2 points in our data. Now, there are a bunch of ways to do this, but 2 are super common. Euclidean distance is the one we all remember from geometry class, right? It's the direct, straight-line distance. But then there's Manhattan distance, which is more like trying to navigate a city grid. You can only move along the axes, like city blocks, so you have to sum up the horizontal and the vertical paths. The second choice is a little more complex. See, once we've merged 2 points into a cluster, how do we measure the distance from some other point to that entire group? Do we measure to the nearest member of the group? The one that's furthest away? The one in the middle? This decision is absolutely critical because it really shapes how our final clusters are going to look.
This is where something called linkage criteria comes in. For example, single linkage is kind of optimistic. It measures to the closest member of a group, which can create these long chain-like clusters. Complete linkage is more conservative. It measures to the furthest member, and that tends to give you more compact, sphere-like clusters. Or you could use average linkage. A really popular one is Ward's linkage, which is pretty clever. It merges groups in a way that minimizes the overall variance, always trying to keep every new cluster as tight as possible. The choice you make here really matters.
So after all that merging and measuring and decision-making, what's the final output? What do we actually get? Well, we get this beautiful and incredibly informative diagram that tells the entire story of how our clusters were built. This awesome visualization is called a dendrogram. You should think of it like the complete family tree of your data. The leaves down at the bottom are all your individual data points. As you move up the tree, the branches show you exactly which clusters were merged and at what point. Now, the key thing to look at here is the height of the branches. A shorter branch means the 2 things that joined were very similar.
And this right here is the true power of the dendrogram. It helps us decide on the final number of clusters. You can literally just draw a horizontal line across the tree to cut it, and the number of vertical lines your cut crosses, that's your number of clusters. A great rule of thumb is to make your cut across the longest vertical line you can find, because that often represents the most meaningful, natural separation between your groups.
So, how does this stack up against another popular method, like k-means? Well, the biggest difference, and it's a game changer, is that hierarchical clustering doesn't force you to pick the number of clusters, k, before you even start. Plus, that dendrogram gives you this rich, easy-to-read story of how the groups were formed. So what's the trade-off? It can be pretty slow on very large data sets, and that's where the raw speed of k-means really shines. So what's the main takeaway here? When should you use this? You should definitely reach for hierarchical clustering when your data set is on the smaller side, when you really want to understand the relationships and the hierarchy in your data, and most importantly, when you have no idea what the ideal number of clusters is from the get-go.
Look, if you remember just one thing from all this, make it this. Hierarchical clustering builds a tree of relationships by merging the closest items step by step, and you choose your final groups by just cutting that tree. It's a truly elegant way to let the data itself tell you its own